Hello guys, and welcome back to my YouTube channel, or welcome if you are new here. In this video, we are going to be discussing electrophilic aromatic substitution. This video is going to be split into 4 parts. In part 1, I'm going to be discussing the electrophilic aromatic substitution, in other words, EAS General Mechanism. In step 2, I will be discussing the effect of electron-donating groups on EAS reactions. In part 3, I will be discussing the effect of electron-withdrawing groups on EAS reactions. And finally, in step 4, we will finish off with some examples. So without further ado, let's get right into part number 1. And I want you to consider benzene. So C6H6, that's the molecular formula. Benzene has 3 pi bonds, 6 carbons, labeling them clockwise, 1, 2, 3, 4, 5, 6, and this is arbitrary. You could label this however you want. This is just so you and I can communicate with one another when I go through the mechanism. Let's make this a little bit prettier. Let's make the 3 pi bonds different colors for when we do the mechanism, so you can track the movement of each specific pi bond. And when we're talking about electrophilic aromatic substitution, so EAS reactions, benzene is our star actor, okay? We're talking about benzene, and the question we're asking is what happens to benzene when you throw in something that is cationic? Well, nucleophiles are nucleus-loving, and they're also negatively charged or electron-rich, so something with lone pairs or pi bonds. Benzene's got pi bonds. We just said there's 3 of them, right? And since opposites attract, nucleophilic things attack electrophilic things. So we're going to look at how benzene reacts with electrophiles. And in part 1, we're going to be going over the mechanism. So let's say you have benzene and you toss in an E+, so something electrophilic, into the mix. Since benzene is nucleophilic, the pi bonds are like sea otters. They can move, they're reactive. So one of the pi bonds can go and attack the electrophile. 2 in. And when all the substituents are hydrogens, so each carbon is only attached to a hydrogen on benzene, you can choose any of the pi bonds to react first. So for the purposes of this example, let's say the pi bond in between carbons number 1 and carbon number 2 reacts first. Specifically, let's say carbon number 2 attacks the E+. What happens? So let's draw in everything that did not change. So we can see that the pi bond in between atoms number 3 and 4 didn't move. Pi bond in between atoms 5 and 6 did not move. Carbon number 2 used this pi bond, the pink one, and it attacked the E+. So draw a bond to the E. It is now E. What happened to carbon number 1? Well, carbon number 1 becomes cationic. Loose electrons become cationic because carbon number 2 took both of those electrons to make that bond to the incoming electrophile. So carbon number 1 becomes cationic. And now I want you to think. No atom at the end of the day wants to have a charge. Charges are very bad. So this carbon becomes very poor. And we're always talking about electrons in organic chemistry. So carbon number 1 is now electron poor. And it's going to want to get electrons because it's in a deficit of them right now. But the awesome part about benzene is when one of the carbons on the benzene ring is cationic, it has very generous neighbors. Neighbors that are willing to lend the cationic carbon money, where the money is the electrons in the pi bonds. They're going to move around. I know what that means. When we move pi bonds, it means we draw a resonance structure. Yes, so let's draw a resonance structure. For example, let's move the 2 electrons in between carbon number 5 and carbon number 6 to over. Once again, draw in everything that did not change first. So the ring did not change. The pi bond in between carbons 3 and 4 did not move. Carbon number 2 still has a bond to the E, and E is just some group that was cationic. It could be any cationic group. And the green pi bond that was originally in between carbons number 5 and 6 is now in between carbons 6 and carbons 1. So that means carbon number 5 lost an electron, and it is now cationic. So label in the carbons again, 1, 2, 3, 4, 5, 6. And now I want you to notice something. We moved a pi bond to in. We filled a deficit, right? Carbon number 1 was cationic, deficit in electrons. Whenever you draw this type of resonance, a 2-over type arrow, the positive charge is always going to skip an atom. So it was originally on carbon number 1. It's going to skip carbon number 6, and it is going to move and end up on carbon number 5. So it goes from 1 to 5. Now 5 is cationic. And now I hope you see that we could draw one more resonance structure. We could do the same thing, but let's react the pi bond in between carbons 3 and carbons number 4. And this will be our final resonance structure. So in the same fashion as we did before, take these 2 electrons and go 2 over. The positive charge is going to skip an atom. This time it would skip carbon number 4. So it's going to move to carbon number 3. Draw in all the bonds that did not change, such as the bond to the E, the pi bond in between carbon 1 and carbon 6. Now the purple pi bond is in between carbons number 4 and 5. And carbon number 3 is cationic. This is all of our resonance structures. So we're almost done the EAS General Mechanism. There's just one more step. And the final step of every EAS reaction is always an elimination reaction. What are we going to eliminate? A hydrogen. Specifically the hydrogen that was originally attached to the carbon that attacked the E+ group, so carbon number 2. We need to eliminate this hydrogen. Why? Well, we want to restore aromaticity. In the very beginning, benzene had 3 pi bonds. How many pi bonds does it have right now? Well, it only has 2. That means we need to make that 3rd pi bond. And how do you make pi bonds? Say, Simone, I remember this from last term. Elimination reactions make pi bonds. Yes, and I would say, yes, good job. Let's draw the elimination arrows. So something in the reaction comes in, doesn't matter what, some X minus, some basic thing. 2 in, 2 over. We get our final product of the EAS mechanism. Redraw in my green and my purple pi bonds. And finally, you get that 3rd pi bond. And you still have the bond to the E group. So what happened? Well, benzene reacted with some E+ because opposites attract. Benzene was nucleophilic because of its reactive pi bonds. But we had to restore aromaticity. So essentially, benzene can grab an electrophilic group and not end up changed. And that is why you may see benzene represented with a circle in the middle. This circle represents the fact that the electrons are circulating just like buzzing bees, constantly moving. And at the end of the day, even after benzene attacks something that is electrophilic, it doesn't change. One of those carbons just grabs the E group and benzene remains aromatic. Bada bing, bada boom, that is it. So in summary, benzene acts as a nucleophile. It attacks some E+ group. In consequence, one of the carbons, a part of the benzene ring, becomes cationic. The other carbons, a part of benzene, say, you know what, I'm going to help you out. So the pi bonds move around. Specifically, we should be able to draw 1, 2, 3 structures where the positive charge is on a different carbon. And then finally, in step number 4, an elimination reaction occurs to regenerate aromaticity. So you draw in that 3rd pi bond, which is formed via an elimination reaction, where the hydrogen that is eliminated is always going to be the hydrogen attached to the carbon that grabbed that electrophilic group. Here it was carbon number 2. And that is the general mechanism and overview for EAS reactions. And this brings me to topic number 2. Sometimes the groups attached to the carbons, a part of benzene, are not always just a hydrogen. The first type of group we're going to discuss is an electron donating group. So in summary, this is some group with electron density. So it's electron rich. For example, it could have a lone pair. This would be a really good, a strong electron donating group, like the methoxy group that we are going to use in this example. It could also just be a basic alkyl group. And now the interesting thing about electron donating groups is when they are on benzene as a substituent and you add in some electrophilic group, before we could choose any of the pi bonds, right? And the electrophile could have ended up essentially on any of the carbons. Well, when there's an electron donating group on the benzene ring to begin with, and an E+ is added to the mix, we actually get something specific. Labeling the carbons, let's label them 1, 2, 3, 4, 5, 6. This E+ is going to either end up on carbon number 2, carbon number 6, which in the case of this example would be the exact same product because of symmetry. So the E+, let's make it blue, is either going to end up on carbon number 2 or carbon number 6. This would be the same product, or carbon number 4. And we are going to call these the ortho, which means right beside me, where I am the carbon with the electron donating group. So right beside me, this electrophile can add, or it can add across from me. So carbon number 4. If you label the benzene starting at the carbon with the electron donating group, the E would add to either carbon number 2 or 6, which is the ortho, or carbon number 4. That would be the para. So ortho or para. And this is always the case. Now the question, I guess, is, well, why? Why does the E, the electrophile, end up on carbon 2, 6, or 4? Why not carbons 3 and 5? There's a few ways to rationalize this. And one way is to draw some resonance structures, because resonance always predicts reactivity. Say it with me. You can answer every single organic chemistry question ever with either the words resonance, induction, or sterics. Here, let's draw some resonance structures of methoxybenzene before we even add in the E+. And let's see what resonance tells us about the reactivity, hence which carbons are going to be reactive. Resonance can answer that question. Let's put this up here in the corner. We're just going to remember that, right? Electron donating groups add E+ to the ortho and para positions. Going to put this in my little memory, or my big memory. But let's redraw methoxybenzene, because we got to draw some resonance structures. I want you to think, for every EAS reaction, benzene is the system. The group attached to the benzene is a substituent. And you are asking, does the substituent make the system more electron rich? Hence, is it an electron donating group? Or does it make the system more electron poor? That would be an electron withdrawing group. But I'm not going to get ahead of myself. We're going to talk about that in part 3. So if I draw some resonance structures, I can find out the answer to that question. So draw in all the lone pairs. Ooh, I see this methoxy group has a lone pair. That means I could push an arrow, a resonance arrow, towards the ring. This is a giveaway. If you're pushing arrows towards the ring, this is an electron donating group. So 2 in, 2, up. Draw your resonance structure. So draw in everything that did not change. The oxygen now becomes cationic because it lost electrons, becomes cationic, hence lec. And labeling the carbons 1, 2, 3, 4, 5, 6. Carbon number 2, with respect to the original labeling, is now anionic. Ooh. Nucleophiles are anionic, or they're electron-rich. Nucleophiles, since opposites attract, like things that are electrophilic. Hold with me, let's draw some more resonance structures. So I could also move these 2 electrons, now in the lone pair, 2 in, 2 up. Where's the negative charge now? I hope you see that it would be on the para position. That's interesting. So now this negative charge is on carbon number 4. So draw a third resonance structure. Where is the negative charge in the last resonance structure? So go 2 in, 2 up. Oh my gosh, it ends up on carbon number 6. So, going back to our original structure, ask yourself, which carbons are nucleophilic, nucleus-loving, so more likely to attack electrophilic things, when there's an electron-donating group on the benzene ring? Well, resonance told me that carbons number 2, 4, and 6 are anionic. So there's an excess amount of electron density at the ortho and the para positions when an electron donating group is on the ring. So since opposites attract, when you toss in some E+, who's more likely to react? Well, carbon number 2 or carbon number 4. And I hope that makes sense, because to be a good nucleophile, you must have charge density. So you don't have to directly have this minus charge, but resonance told us that there is more electron density on these positions. So therefore, the ortho and the para positions are the carbons that are more likely to attack the E+ in an EAS reaction, which is why you get ortho and para products when you have an electron donating group on the benzene ring. And now this brings me to topic number 3, electron withdrawing W groups. And we learned in the last part that electron donating groups substitute to the ortho and para positions. So now we got to figure out, when you have an electron withdrawing group on the ring, what carbon grabs the incoming electrophile. And we're going to find out that something different happens than in the last example. When an E+ adds to benzene when an electron withdrawing group is on the ring, the group actually adds to the meta positions. So let's say you toss in this E+. Let's label the carbons 1, 2, 3, 4, 5, 6. The meta positions are going to be positions 3 and positions number 5. So the E+ is going to end up on either carbon number 3, E, NO₂ does not move, or carbon number 5. In other words, the meta positions. But in this example, well, adding the E to either 3 or 5 results in the exact same product, and this is due to symmetry. So now the question is, why? Why does the E+ add to carbons number 3 or carbons number 5 when you have an electron withdrawing group on the ring? And the way we're going to rationalize this is by looking directly at the EAS mechanism. And we're going to say, well, what if carbon number 2 attacked the electrophile? and let's say the E plus tried to add to the ortho position, what would happen? But before we draw the mechanism, let's list some common electron withdrawing groups. So you could have an NO₂ group, or you could have some carbonyl group. And now the question is, well, why are these groups both electron withdrawing groups? It has to do with the first atom attached to the benzene ring. If this first atom is delta plus or positively charged, it is an electron withdrawing group. Why? Well, because if you're in an electron deficit, that means you want electrons. So you're going to try to take electrons from the thing that's electron rich, the benzene ring. So since electrons are moving away from the benzene ring towards the group that is in a deficit of electrons, it would then be an electron withdrawing group. So it's all about the first atom that's connected to the benzene. If that atom is delta plus or positively charged, you most likely have an electron withdrawing group. But NO₂ and a carbonyl are the most common groups that you're going to encounter. Let's keep this information in the back of our minds up here, right? This is what is going to happen. And to prove why the E is not going to add to the ortho position or the para, let's just try to add the group there and see what happens, okay? So labeling our carbons 1, 2, 3, 4, 5, 6. Let's add in some electrophilic group, and let's try to add it on to carbon number 2, and let's see what happens. So carbon number 2 attacks the E+. Why is this bad? So draw in everything that did not change. The NO₂ is still on carbon number 1. The E is now on carbon number 2, and carbon number 1 becomes cationic. And now the question is this carbon stable? So is carbon number 1, the cationic carbon, is it stable? Well, I mean, the pi bonds, the neighbors, could help it out, right? I mean, that would be correct, but what I really want you to look at is how the electron withdrawing group specifically affects this cationic carbon. So since this nitrogen is in an electron deficit, it is positively charged. If opposites attract, like charges repel, you have a positive charge right beside a positive charge. This is a terrible, terrible interaction because like charges repel, oh my God, like charges, you have a cationic nitrogen and a cationic carbon right beside one another. This is not stable. This is terrible. Therefore, E pluses do not add to the ortho position when you have an electron withdrawing group on the benzene ring. So we could do the same thing for the para position. Let's look at resonance and see why the E plus doesn't add para. So let's say carbon number 4 this time, with respect to our original labeling. Carbon number 4 attacks the E plus. So carbon number 3 would become cationic. The pi bond in between carbons number 5 and 6 stays the same with the pi bond in between carbons number 1 and 2. The E added to carbon number 4, and carbon number 3 is now cationic. So right now I don't see an issue yet, right? But let's draw a resonance structure. So the neighboring carbons, they want to help out the cationic carbon, right? So this pi bond is going to go 2 over. So now let's draw the resonance structure. Oh no, look at what we get. The positive charge now goes to the carbon with the NO₂ group. Carbon number 1 is cationic again after you draw your first resonance structure. So this is, once again, not stable. Therefore, E pluses do not add to the para or the ortho position when an electron withdrawing group is on the benzene ring. By consequence, what carbons are reactive? So these are both bad. So by consequence, the carbons that are reactive when you have an electron withdrawing group on the benzene ring are carbons number 3 and carbons number 5. That is why you get an E+ adding to the meta position. And this would be the product of your EAS reaction. So that is it, that is all. Now, before we move to part 4 and do some actual examples, let's summarize everything we learned about electron withdrawing groups and electron donating groups. So the easiest way to summarize something is to make a table. So you have your electron donating groups and you have your electron withdrawing groups. So examples of electron donating groups are any OR group. And I'm going to draw a line and a squiggly line where over here you would have the benzene ring. Other electron donating groups could be any nitrogen with an R group or any alkyl group, like a tert-butyl group. Electron withdrawing group examples are NO₂ groups or any carbonyl groups or even something like a CF3. And once again, it solely has to do with the fact that this first atom, the nitrogen, the carbon, and the carbon, are either positively charged or delta plus. Whereas in the electron donating groups, the first atom connected to the benzene either has lone pairs, like the oxygen or the nitrogen, and this would be an NR2, where the R's could be any group. So now you could say, well, this carbon, a part of the tert-butyl group, does not have a lone pair. So why is it an electron donating group? This can be rationalized by looking at the exact same thing that happens with respect to our carbocation stability trend when increasing the amount of alkyl substitution. We said a 3' carbocation is more stable than a 2', which is more stable than 1'. Why? Well, because these CH3 groups are electron donating. They donate electrons to that central carbon. They help out the carbon. So that means these 3 CH3 groups are electron rich, so they're donating towards that central carbon, meaning that that carbon, the blue carbon, the central one, is not in an electron deficit. It is in fact electron rich because it has electron gun throwing groups attached to it. So when you have an electron donating group on the benzene ring, so electron donating group, your products are always addition to the ortho or the para, where the ortho stands for right beside me, and the para is right across from me, where me is the carbon with this donating group. So E would go either there or there if you have an electron donating group on your benzene ring. The opposite happens if you have an electron withdrawing group on your ring. Electron withdrawing group. If you want to add in some E+, the E+ is going to add to the meta position, where the meta position would be, if you labeled these carbons 1, 2, 3, 4, 5, 6, where carbon number 1 is going to be the carbon with the electron withdrawing group. The E+ is going to add to either carbons 3 or 5. And this would be the meta position. So ortho, para for electron donating groups, and meta for electron withdrawing groups. Without further ado, let's do some examples. We have now prepared for battle, and the battle is doing these final practice problems. All right. Question number 4, part 1, is going to be when there is an electron donating group on the ring. And in part 2, we're going to do the same thing, but if an electron withdrawing group was on the ring. So, let's say you have methoxybenzene. Very classic example. You will see this group a lot. So remember, it's an electron donating group. So electron donating groups, where do they direct the electrophile? They direct to the ortho or the para positions. So if you're adding in some E+, just add this group to the ortho or the para positions. And the nice thing about drawing the product is you can just draw a circle in the middle of benzene, draw on your original electron donating group, so the OME, and all you need to do now is add in the withdrawing group to the ortho position, so the pink carbon, NO₂, or your para product. So the para product would be if you added in the NO₂ group to the green carbon that I highlighted. And once again, just draw that circle, which you're telling the marker that you know that aromaticity is preserved. And you add in that NO₂ group. And that's literally it. You just need to figure out, is this a donating or withdrawing group? If it's a donating group, you just draw a line, one single line, make a bond to the incoming E+ for the ortho and the para positions. So what about if we added in this electrophile? It looks a little different than the NO₂+. So same thing. Draw in your benzene with the OMe group. Draw a circle in the middle. You're saying aromaticity is preserved. You're going to add in the terp-butyl group to the ortho, so the pink or the green carbon. So now do not add or drop any carbons. So you're making one new bond, and you're making a bond to a central carbon that is attached to 3 other carbons. So just like that. That would be my ortho product. Then my para product would be if I drew the same group on the green carbon, so the carbon across from the carbon with the OMe group. So once again, draw in a new bond, and then draw in that E+ group. This would be your para product. And that is it, that is all. But now you could get asked a question that's a little bit more complicated. You could say, so for part B, question 4, part 1, part B, would be consider the addition of one more equivalent of the same reagent. So in the top example, we're adding in NO₂, one equivalent in the beginning, and then one equivalent in the second part. In the bottom part, we're doing a terp-butyl group once, and then twice. For the purposes of this example, let's only consider the para products, okay? So we're only going to consider the para products, where the para products are conventionally better because of a decrease in steric hindrance with respect to the groups on the ring. The groups on the ring in the para product are farther away from one another than they are in the ortho product. So this is a good thing because groups want to be far away from each other. So just considering the para product, we are now going to ask which reaction is faster. Is reaction 1 faster or is reaction 2 faster? So what would be the product? Well, the para position is already occupied, right? So draw in everything that is already there. So the OMe is still there, the NO₂ is still there. Who are you going to listen to? Are you going to listen to an electron-withdrawing group? Or are you going to listen to an electron-donating group? Well, what type of group makes benzene more nucleophilic? Donating groups. So you pretty much do not care that the NO₂ group is there. You still listen to the donating group. So this new group is going to add to one of the ortho positions. So let's add the new NO₂ group to the ortho position, for example, carbon number 2. So the new NO₂ group goes there. That's it. What about the bottom example? Well, same thing. This new group is going to listen to oh wait, they're both electron donating groups, right? Electron donating group. You say, Simona, oh no, what now? You listen to the better electron donating group. So since the methoxy group has lone pairs and the terp-butyl group does not, the electron donating group that is a better director is the methoxy group. So you would add to one of the ortho positions with respect to the methoxy group. So our new terp-butyl group, the second equivalent, would add to one of the ortho positions with respect to our methoxy group. And these would be your products. But we haven't answered the question yet. The question was, which reaction proceeded faster? Reaction number 1 or reaction number 2? The answer is reaction number 2, because which benzene was more nucleophilic? In summary, whenever you have more electron donating groups attached to the ring, benzene is more nucleophilic because it has more electron density, hence it's a better nucleophile. It's more likely to attack something that is electrophilic, so positively charged. Whereas in the above example, we had a withdrawing group. So what did the withdrawing group do to the nucleophilicity of the benzene ring? Well, it would have decreased the nucleophilicity of the benzene ring. So in other words, 1, 2 electron donating groups on a benzene is much better than having only one donating group and an electron withdrawing group, because donating groups make benzene more nucleophilic. Increase the charge density, and they make benzene more nucleophilic. Hence, this reaction would proceed faster. So now to finish off this video, let's do the exact same thing, but this time we have an electron withdrawing group on the ring. What happens now? So you have to ask yourself, where does an electron withdrawing group add E pluses? Well, it adds it to the meta positions. So if we label the carbons a part of the benzene ring, 1, 2, 3, 4, 5, 6, where you are labeling carbon number 1 as the carbon with the withdrawing group on it. So all you need to do is add this E plus to the meta position. Draw in everything that was originally there. So the benzene with one NO2 group on carbon number 1, but now you got to put an NO2 group on carbon number 3. You also could have chose carbon number 5, but in the case of this question, you're going to get the exact same product. So now what about when you add in a butyl group? Well, same thing. It just adds to the meta position. So draw in everything that was originally there. And now draw in your tert-butyl group on the meta carbon, one of the meta carbons. So let's say carbon number 3. So now we're going to do the same thing as we did in the last example. Considering this product, add in one more equivalence of the respective electrophile. Which reaction, reaction 1 or reaction 2, proceeds faster? And what's your product? In the top reaction, so the green reaction, we added in an NO2 group. So when we add in another equivalence of something, since these are both electron withdrawing groups, the only position that this NO2 could add would be the other meta position. So carbon number 5, which is meta to both electron withdrawing groups. So the NO2 group would go to carbon number 5. So you now have 3 NO2 groups on the benzene ring. And this would be your product. And I hope you would be able to tell me that this reaction would be very slow, because when you have 2 electron withdrawing groups on a benzene ring, well, this decreases the nucleophilicity of the benzene. So it's not very reactive. It still does end up reacting, but its nucleophilicity is decreased. So decreased the nucleophilicity, therefore, is the slower reaction. But now, what are the products for the blue reaction? So when you add in a tert-butyl group, we haven't seen this yet. Now what you have is you have both an electron withdrawing group, and an electron donating group on your ring. So who do you listen to? You always listen to the better director, where donating groups are better directors for benzene because they increase the electron density at the benzene ring. So relabel the benzene with respect to the carbon with the donating group. 1, 2, 3, 4, 5, 6. What are your ortho positions? Well, your ortho positions are carbons 2, 6. Oh, I have to draw a product where this new E plus group is on each of those carbon groups. So product number 1, let's add it to carbon number 6. And this time I'm going to need to draw 2 ortho products, because the 2 ortho products that you're going to get are not symmetrical. So I need to draw them both. Let's draw the second equivalence of the tert-butyl group in purple. So your first ortho product will be this, where the purple tert-butyl group added to carbon number 6. Your second ortho product is going to be when the purple tert-butyl group adds to carbon number 2. So that's the other ortho position. And then finally, your para product is going to be when the purple tert-butyl group, say it with me, adds to the para position, so carbon number 4. These are your ortho products, and this is your para product. And now some people might say, and this is an advanced component of this question, if I was giving this as a test, this component of the answer would be a bonus mark. Your main 3 products were these 3 products, 1, 2, and 3. But is a terp-butyl group a really good electron donating group, like the methoxy group? Well, no, because we can't draw a resonance structure. It's only an inductive donating group. So that means you might get a product, and it's most likely the most minor product, where the incoming E+ would have listened to the electron-withdrawing group. So you might have a very minor product where the terp-butyl group would have added to carbon number 3. So the meta position with respect to the original electron-withdrawing group. So carbon number 5 with respect to our original labeling. And these would be your 4 products. But once again, this product, in my opinion, would probably be a bonus mark if this was on your test. The main thing that we would want you to see here is that you are going to listen to the donating group, and you are going to have to draw an ortho, well, 2 ortho products and 1 para product. And finally, your final answer would be which reaction was faster, reaction number 1 or reaction number 2. And reaction number 2 is much faster because there's an electron donating group on the ring, where donating groups increase the nucleophilicity of the benzene ring, and they increase the probability of the benzene attacking the incoming E+. So this reaction is faster. This is faster than when you have 2 electron withdrawing groups on the ring. All right, that is it for what I had planned for this video. I hope this was helpful. Make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. It really helps me out, and it also helps students just like you have the potential of seeing my videos. I hope you have a great day. Let me know if you have any questions down in the comment box below. Bye!